So today I'm going to talk to you about spinning lignin. We're using two different methods. One's a solution-based method, and then the other is a melt extrusion. But first, I'd like to recognize a number of my co-authors, basically the folks that did the work, and so past team members and current team members, and so got to work. All right, excellent. So Mi-Jung Cho, Ricky Hua, Mustafa Karazlan, Liang Lu, and Sanaa Sabagi. And so a lot of the work that you see, it's from their hands. So I'm going to begin just reviewing a little bit about kraft lignin. And so that's a nice introduction to lignin that we just saw earlier. And so kind of going to remind, again, I agree, a very heterogeneous type of material. It is a polar organic polymer. And so we're going to then discuss how we can spin lignin using solution methods, and so a lot of times we need a little bit of a helper polymer in order to do this. And then along the lines of this kind of water fiber interactions, when we spin our lignin fibers using electrospinning, we can actually redisperse those into a water suspension, and then we can actually make new three-dimensional materials out of them. And so I'll highlight some of that work. And then we'll change gears and talk about basically industrial processing in terms of being able to put lignin into different melts and being able to make a relatively uniform fiber using that process. So kraft lignin, very different from native lignin. And so we actually know a lot about native lignin, even though we don't know everything, since the whole issue of once you remove lignin, you begin to change it. But we know that within native lignin, I look like this little diagram here, we have lots of nice carbon-oxygen bonds. But as we go through this process with kraft pulping, we end up with lots of carbon-carbon bonds. And so just this idea that we're cooking wood chips at 170 degrees in aqueous alkali. So there's actually a lot of heat-induced changes just by heating wood to that temperature, and so there's lots of actually lignin degradation occurring there. But then the sulfide-induced alkyl bond breakage, so we have lots of actually free phenolics developing in this process. So the nice thing about lignin today is that there's a number of places where you can get some industrial lignin, and so there's the ligno-boost process, and then there's also the ligno-force process that happens with CO2 precipitation, and also the indolent AT formerly, as well as CO2 precipitation. So lots of lignins out there in the market. We're actually still missing a lot of information about the kraft lignin. And so there's a really nice study where they used a labeled lignin in order to understand some of its structure after doing the kraft pulping process. And they actually found 45% of the structure being able to identify that structure after doing this kraft pulping. But 55% of the structure is unidentified, right? And so that really means that we don't know exactly what's in these technical lignins. And so I like this quote in the paper. It says, 100 new linkages can be developed from breaking a beta-4 bond. So lignin's really complicated. I'm not sure if we'll ever know what the technical lignin really looks like. But it is polar. It has these mixed functional groups, aliphatic hydroxyls, phenolics, and also lots of, not lots, but some carboxylic acids. And so it is a polymer, but there's also a debate about what it looks like in solution. And so we recently took softwood kraft lignin. We then split it up into an acetone soluble and acetone insoluble. And so I'm going to talk about acetone soluble lignin and insoluble lignin throughout this presentation this morning. But then we actually fractionated it with membranes. And so then we tried to actually look at what type of shape these lignins have in suspension. And so we determined the Markov Saccharuda parameter, the alpha parameter. And so if you see this diagram here, you have this alpha value with different types of structures. Oh, And so if you have this alpha value of around 0.5, you have this random coil. And so that's a lot of times when we, from a polymer science perspective, we think about linear polymers. We have this nice 0.5 value. And so basically as molar mass changes, you have actually a change in your coil size. Lignin, though, really doesn't behave like that. And so it's actually a very compact molecule. The acetone-soluble lignin is extremely compact over here. It actually has essentially like an Einstein sphere type value. The acetone-insoluble material has a slightly higher value. And so there's actually some work that talks about how you can have a self-avoided sheet like graphene oxide having a value of around this 0.33. So essentially, we don't have a molecule that can reach out and grab another molecule and entangle together. They can associate, but most likely you don't have this entanglement with when we're working with lignin. So because we don't have entanglements, we need some help. And so in order to spin fibers, we actually have to put some additives in there. We don't actually need a lot of additive, but we need some. And so if we put a higher molar mass helper polymer in with the lignin, basically you can lasso lots of different lignin molecules together and basically provide a little bit of entanglement there. If you use higher molar mass lignin as well, you can usually spin slightly better fibers using the solution spinning method. And so my personal opinion is that it's because you're actually building more contact area and around the outside of the fiber. There's actually a really nice study looking at polyethylene oxide interaction with lignin using a SANS technique, and so you can certain polymers can interact with lignin very nicely. But if we go to melt spinning, we essentially are really reliant on the polymer that we're trying to mix lignin with. If we try to melt lignin itself, it ends up with a very brittle kind of material, and so we're reliant on this other type of blend component. And really, in order to get the blend components to work, you usually have to turn off a lot of the functional chemistry with lignin, and so we can go ahead and modify the lignin using that method, a number of different methods that we'll talk about today. So we use electrospinning a lot within our lab, and so this is a very simple setup where we have lignin that's dissolved in an organic solvent. And so once we dissolve lignin in the organic solvent, we can load it up in a syringe. And so then we can apply a voltage between the tip of the syringe needle and a collector. And so we have the differential there. So at the tip of the droplet, you have a little cone that forms, and then that's pulled towards your collector. And so you end up actually making a really nice non-woven type of mat of lignin fibers there. And so here's a couple images of what that jet looks like. It's not just a single fiber that's being propelled. But as that jet elongates, it elongates very quickly. And so what that means is that you can have some orientation because of this fast elongation. And so here are some fibers that we made from 99% lignin. And we actually see this birefringence related to some orientation of that lignin. And so there's a couple of reasons why we want to make nanofibers. One is their very high surface area, not as high surface area as, say, some aerogels, but higher than other types of fibers out there. And the other reason is actually can enhance the mechanical properties. So if we take that lignin spinning dope and just cast a film with it, we can see over here where lignin, once it dries, it's very brittle, it just flakes apart. But if we actually can spin a nice nanofibrous mat, then we actually end up having a relatively flexible mat where we can actually roll it and bend it. And so just when we make a very skinny fiber, the bending rigidity of that fiber basically allows you to have more motion on it. So within our group, we've used two approaches. And so one approach is making a very high lignin content fiber. And so basically the story behind making high lignin content fibers is that fractionation helps. And so this idea of lignin is a very heterogeneous polymer. It's true, and so if we can get a higher molar mass material, then we actually can have more interactions, and then we can end up making a more actually smaller diameter fiber. We can get up to 99% lignin with about 1% with about 1% polyethylene oxide in it. The drawback is that you need organic solvent, and so if you're doing electrospinning, trying to scale that up, you'd have to capture that organic solvent and then recycle it. So we've recently done more water-based processing, and so this is not something that we've developed, but it's something that we're using. And so actually, Orlando, I think when he was here at Alto, did lots of electrospinning with water-based solutions. Again, fractionation helps. Fibers can be spun up to about 85% lignin in it, and so you need some pH adjustment, and so then you're stuck with a little bit of salt within your fiber. But then as you're spinning, you need lots of relative humidity control because that solvent just evaporates as you're spinning, and so you need to actually have that water removed. So here's two graphs of some electrospun fiber from water, and so on the left side is this fiber diameter as a function of spinning dope concentration down here, and this just shows basically these different points show differences in fiber diameter. But if you look closely, all these fibers are terrible, actually. They're beaded, they kind of have this rough surface morphology. And so what we have to do is actually do fractionation before we spin. And so if we use a membrane fraction, we can then actually create lignin. Different lignin contents all have very uniform fibers. And so this is great. And we actually started to make some mask materials. And so these electrospun fibers, they're great. They actually have a very high quality factor. And so that means a very high rejection rate of very small particles, and then also a very small pressure drop from one side to the other. And so we're working with a couple companies, lignin-based companies, trying to develop some of these kind of lignin-based mask materials. So we also use solvent fractionation, and so kind of coming back to the talk before me, we actually use dry acetone, and so if we use dry acetone, we can't dissolve all the lignin in it, and so we're getting 40–45% of the lignin dissolved in acetone, and you can just filter it, and so then you're left with two batches of lignin, acetone soluble and acetone insoluble. If you look at the molar mass, here in the middle, we have this original lignin in green. If we look at the acetone soluble, it's coming out at higher retention times, and so it's lower molar mass. The acetone insoluble is actually slightly higher molar mass. And we've done lots of chemical analysis, both 31P NMR, 2D HSQC NMR, and really the big difference between the two is the acetone soluble lignin has more phenolics. The acetone insoluble material has slightly more native linkages, and so not a ton, but more than the acetone soluble lignin, and slightly more aliphatic hydroxyls. And so this actually has a big impact on properties. So we took this softwood kraft lignin, we split it up using acetone, and then we actually could spin fibers from both the acetone soluble and acetone insoluble material. And so these had very different properties, and so on the one side down here we have electrospun lignin fibers, and if we use acetone soluble lignin, we actually end up with a very hydrophobic mat. And so if we use acetone insoluble material, our material is actually very hydrophilic, and so it's not the best surface for official analysis because you have lots of air trapped underneath your fiber, and so that's why we get such a hydrophobic type material here. And then at the same time, if it's slightly more hydrophilic, it's going to pull and wick that water into it. But really the big thing I want to point out here is that we have acetone soluble kraft lignin. And so what we have is the storage modulus as a function of temperature, and so we're taking these mats and we're putting them in the DMA, and so we're looking at the mechanical properties. We can see that we go through a TG and then actually decreases. For the acetone soluble lignin, that TG is much higher, it's closer to 200 degrees, and there's only a small decrease and then an increase. So, and if we look at the softwood kraft lignin, it's actually a combination, the TGs between the two, and then you have a decrease, but then actually you have an increase in modulus. And so I'll talk about these pictures in a couple slides coming up, but basically the story is that acetone soluble kraft lignin can actually flow like a liquid, and the acetone insoluble one can't. And so this is just a quick kind of a little bit of data about basically the hydrophobicity or the hydrophilicity of these mats. And so, but what I really want to point out is that if we take this acetone insoluble kraft lignin fiber, it's wettable. It doesn't dissolve in water, but it is wettable. And so we can take this fiber mat and disperse it into water. And so once we disperse it into water, we can actually fragment the mat into individual fibers, and then we can actually make new materials from that. So this is kind of a busy slide, and so if you give me 2 seconds, I'll walk you through it. All right, and so this idea is that we're electrospinning fibers, we're putting the mat into water. We're using just vortexing that can shake apart the fiber mat, and so once we do that, we can then freeze dry this mat, and so we're left with kind of like a cryogel type material. It's a foam, and then the secret is doing some type of thermal treatment in order to actually get some of these fibers to lock together. And depending upon the type of lignin that we're using, we can either get the spot welding, or we can actually get pretty good these interconnected fibers. And so this just shows an example of it's a relatively porous type of material, and so it's actually really lightweight, and so it's 10 to 20 milligrams per cubic centimeter, right? It's extremely flexible, and so remember this is 99% lignin with 1% polyethylene oxide in it, and it has a shape memory effect to it. And it actually, after you do some heat treatment to it, it becomes more hydrophobic, and so then you actually can use it for water and oil separation. So why is that kind of compressible? And so if you look at the freeze-dried material here, actually almost has an unhappy face on it, right? And so 2 eyes and a little frown there because it knows it's about to get squished. And so if we squish it, it doesn't come back up, right? And so really what happens is that we need to exploit the thermal properties of the lignin in order to actually have some cross-linking together. And so what this DMA graph down here shows that we're actually ramping up temperature to 250 degrees, and then we hold it. And after we hold it, we are allowing some cross-linking of the lignin mat to occur. And so this is done in a parallel plate type of geometry, and so you have some compression of your mat when we're studying this. And so we actually have a slight increase in storage modulus right before the TG, and then that declines at 180 degrees or so. And then once we hold it at 250, we can see the mechanical properties increase again. And so this shows that lignin is acting both as a thermoplastic, but then it's also acting as a thermoset. And so we're exploiting that idea around lignin being a thermoset. So again, this is one more complicated kind of graph that I'll walk you through. Instead of just using one type of lignin, let's say the acetone insoluble, or this other type of lignin that we call F4, that's equivalent to acetone insoluble lignin, we're combining a certain amount of acetone soluble and acetone insoluble lignin together. And so we actually are also putting some additives in there, like cellulose nanocrystals, that can help with the rubbery plateau when we're trying to cross-link it. But I just basically want to draw your attention to this graph in the middle, where we have compression stress as a function of compressive strain. And so there's actually 3 different graphs here. And so that green one is when we only use lignin like the acetone insoluble lignin that has a very high TG. It only has a compressive stress up to maybe about 4 kilopascals. If we're able to put the right amount of acetone soluble lignin in it, and so modulate that TG a little bit, we actually can get more fiber-fiber kind of interactions. Instead of just the spot welding here, we actually end up getting these nice cross-sectional areas. And so if you look at this red graph here, it spikes up to almost 20 kilopascals. And so we can use the thermal properties of the lignin and manipulate it. So we're doing a lot more of this with these materials. Like you can carbonize them, you can have freestanding supercapacitor electrodes, things like that. And so a lot of neat stuff that we're kind of moving forward with. Coming back to this idea of the thermal properties of lignin, exploiting them. And so kraft lignin, really, if you heat it up, it's not going to have liquid-like behavior. And so in order to melt process something in an extruder, you need it to behave like a liquid. And so what this graph shows you is this basically, again, this compressive DMA analysis where we're looking at tan delta as a function of time. And so these plates are heated to 180 degrees. And so if you have a loss modulus that's greater than the storage modulus, you have a value greater than 1. And usually that's when you begin to have liquid-like behavior. And so if we look at the axis here, we see this 1 value. And so the acetone insoluble kraft lignin has this value below 1 the whole time. The acetone soluble kraft lignin in the blue value here has a value much greater than 1. Right? And so then we can now also do things like esterified lignin, and so that can change the thermal properties of lignin a bit. And so we can see that we can get a little liquid-like behavior, at least in the beginning, if we have esterified lignin. But then coming back to our DMA experiment earlier, this is in tensile mode with the electrospun mats. We can see that before and after the experiment, we actually have this collapse of the lignin because it's actually beginning to flow. And if we actually look at the center section here, no longer has individual fibers, but all those fibers have come together. I'm going to go into fast forward mode here. So 2 minutes to go through the rest of this melt lignin, but essentially if we're talking about making blends with lignin, we're trying to mix it together. We can either have basically a mix or a blend. If we have a mix, we have basically distinct phases. What we want is actually a blend with our lignin. So what we do lately is doing a chemical modification of lignin, and so we use this reagent called ethylene carbonate. It's actually a nice CO2 storage molecule, and so if we ionize lignin with an alkali catalyst, we can take all those phenolics, all the carboxylic acids within lignin, and convert them into these hydroxyethyl groups. And so this kind of just shows lignin has these different types of functional groups. You can see the P31 spectrum here. And so after this modification, we only have these aliphatic hydroxyl groups. And so that's great because then we can chemically modify them in other ways, like using esterification. Without acid chlorides, we can just use organic acids. And so it works great with a number of different organic acids. And so we do a lot with propionic acid, but then we also use other acids like 5, 8, and 18 carbon acids. Even we've used a formic acid down here, and so it's very effective. And so then we can use this modified lignin to actually mix with things like polylactic acid and also with another polymer called Ecoflex. And so that's a polybutylene adipate terephthalate. And so I'll turn my little video on here. And so this is this idea of putting a little bit of lignin into our extruder with these compostable plastics, these biodegradable polyesters, and so we can get them to mix pretty well. And that's just the kind of the process showing there. If we take unmodified lignin and put it in with these polymers, we actually see the kind of this phase separation. If we use acetone soluble lignin, we actually have slightly better basically movement of the lignin. And then our esterified lignin, we actually have really good blends. And so we looked at some DMA data. And so really what I want to point out here is that we actually do have a shift in TG of the PLA with just a little bit of lignin in there. And so there is these interactions between the lignin and the PLA. We can look at the mechanical properties, and so the smaller the fiber diameter, and so 80, 75, 117, we actually have kind of a jump in the mechanical properties. And so knowing that we can kind of change the fiber diameter, what we did was draw these melt-spun fibers at a certain temperature, and so 4 times the initial ratio, we get a change from, say, 100 microns down to 60 microns, and so we have a significant jump in the mechanical properties. And so if you look at the graph here, we see the PLA and the PLA with a little bit of lignin in it, both on stretch, has 1 value, but as soon as we go ahead and draw it, we actually have a great increase in the mechanical performance with these. And the great thing is adding lignin in it doesn't mess up the system. And so we actually get a little bump, but also that could be because the fiber is slightly thinner as well. Why do we get such a nice bump? Part of it is that we're getting some orientation within the fiber, and so this is our PLA fiber under a cross polarizer. We can see after drawing we have more orientation of our material for both our PLA and then also the one with a little bit of lignin in it. So lots of take-home messages about lignin fibers, but I think I'm almost out of time. So basically the key is that kind of two things. One is we can do fractionation, and that can help spin fibers, and that actually helps both the solution spinning and also the melt spinning. So thanks for the funding and the folks that also helped out with some of the work.